menyampaikan lecture-nya. Dan kepada teman-teman, mari kita simak, dan bagi mahasiswa mari silakan dicatat dan diambil sebagai bagian dari kuliah kita yang kita adakan setiap pekannya sebelumnya. Dipersilakan Pak Profesor.
Oke, terima kasih ya. Assalamualaikum warahmatullahi wabarakatuh dan selamat siang. Jadi insyaallah saya akan berikan linknya ya, link untuk notes-nya. Bentar ya. Linknya ada di dalam chat ya. Jadi linknya itu bisa saya mungkin minggu depan saya akan buat sedikit perubahan kepada nota tu. Jadi tak perlu nak save dan print ke apakah. Jadi gunakan yang terbaru sekali. Ya. So only the latest ones. Baik, insyaAllah kita mulakan. Kalau di Malaysia itu dibilang kuliah lah.
Sama.
Ya.
Kuliah juga.
Jadi insyaAllah kita mulakan kuliah untuk subjek elektronik spektroskopi ini. Yang sebenarnya saya sudah lama ini meninggalkan subjek elektronik spektroskopi ini. Sudah hampir 10 tahun ya. Lebih 20 tahun saya mengajar subjek ini di peringkat asas dan advance. Jadi agak susahlah untuk di concentrate dalam 2 jam kan. So it took me a lot of effort to do this, to actually concentrate everything in 2 hours, and I don't think I can finish it. But anyhow, with the notes, I hope students or listeners can always refer back to the notes, and you can do your own revision lah, or referencing. So we will start with electronic spectroscopy. So in UM, when we teach electronic spectroscopy, we start off with the atomic spectroscopy. And because to me, I always look at spectroscopy as the practical subject of quantum mechanics. So in order to understand spectroscopy, unfortunately, we really have to understand quantum mechanics, because there are a lot of, when we do analysis on spectroscopic phenomena, especially electronic spectroscopy, there are a lot of, you are assumed to have some basic understanding of quantum mechanics. This is especially so when we talk about term symbols, when you talk about labeling of electronic states, because you can understand spectroscopy in 2 ways, either understanding it in a totally qualitative manner. Artinya, for example, if we talk about an electronic transition, we'll be talking about, say, pi to pi star transition, for example, or n to pi star transition. So we leave it at that. So we say that, okay, this peak is due to n to pi star transition. But if you look at spectroscopic books, most of the treatment is actually done in a rather, semi-quantitative, semi-qualitative way. So rather than talking about n to pi star transitions, we will be talking about, say for example, T 2G to EG transition, for example. Yeah. So some symbols that if we were unable to understand quantum mechanics, we don't have the basics of quantum mechanics in understanding spectroscopy, we may have trouble. We can just accept it, which is not a problem, and think of it as a qualitative assignment, for example. But I think it would be nice to know what's going on behind it and to understand how these symbols actually came about. So the orientation that I will be looking at in these lectures will be sort of quantum mechanics practical approach. So there will be, I won't be looking at the actual quantum mechanical calculations. We will be looking at some of the examples later on, because quantum mechanics is, we don't calculate using pen and paper anymore. We use Gaussian and stuff like that, all these programs. So we will be looking at or trying to understand how Gaussian interprets spectroscopic phenomena, and maybe we look at how we can sort of apa ya perkataannya? That means we try to compare lah, the theoretical prediction of computational chemistry software and the actual spectroscopic phenomena, actual spectroscopic observation. Yeah. So we'll be looking at some rather quantum mechanical oriented lectures. Yeah. But it's okay. I will try to make it as easy as possible. Well, I am still learning. There are still a lot of things that I don't understand. But whatever I understand, I will try to convey to all of us and see if we can actually gain something from this. There will be things that you have already seen and done, and there will be things that are quite new. When I first prepared for the lectures some years ago, a lot of things are quite new to me, because during the undergraduate years I did not learn it. Yeah? So I learned things like, for example, in a qualitative manner. Then suddenly, when you look at the books, you get quite a surprise, you know, because we are chemists, we're not physicists. We've never seen a lot of the things that are discussed in the book, so we have to relearn and you know, get new knowledge out of it. So we will try to see if you have already seen it, if understood it, alhamdulillah, it is good. But for those who haven't, I will try to make it as easy to digest as possible. Okay. Right, electronic spectroscopy is general to all systems, atoms and molecules. But the way we treat atoms and molecules are quite different. So we will look at the atoms first. We look at electronic spectra of atoms first. And of course, the simplest atom is hydrogen atom. And we will look at how quantum mechanics actually deals with hydrogen atom. It may look simple, but it turns out to be quite involved. Yeah. So in order to understand bigger atoms with more electrons, we have to understand how it works for atoms like hydrogen. Yeah. Okay, so first of all, when we talk about quantum mechanics, we have to talk about the Schrödinger equation. So for any system, be it an atom or be it a particle, in chemistry, quantum mechanics syllabus, we teach students, say for example, on the how to solve the particle in the box problem. Yeah. So that one consists of only one particle. Then we go up to hydrogen atom, which consists of one electron and one proton. And of course, one electron and one proton, like hydrogen atom, the solution is very, very involved. It's much more complicated to the one particle system. So we will look straight into the solutions for the Schrödinger equation of hydrogen atom. So as chemists, usually we are not really interested in how to solve the problem. We are interested to see the results, and we actually apply the results to the problems that we are interested in, and actually see if we can actually solve the problem we are interested in with the results of quantum mechanics. So the Schrödinger equation for atoms, basically when we solve the Schrödinger equation, we get two things. We get the energies of the system plus the wave functions of the system. Yeah. So it's energy, a set of energies, and a set of wave function. The wave functions consist of some fundamental constants, h, c, m, the coordinate of the system, coordinate of the electron, for example, with respect to the center, which is the nucleus. So we have a coordinate of x, y, z, r, but usually when you solve the hydrogen atom system, we are not using the Cartesian coordinate, we are using a different coordinate system.
Sorry, shall we share the screen?
Pardon?
Boleh share screen atau kita share yang PowerPoint-nya?
Ya, kenapa? Boleh apa?
Share screen.
Share, oh belum share, subhanallah. Subhanallah, sebentar.
Okay.
Okay, sudah nampak ya?
Sudah. Okay.
Terima kasih, saya tak tahu tadi. Baik. Jadi Schrödinger equation for atoms ini, when we solve it, we get psi, wave function, and the energy. So wave function gives us some idea of where the electrons are in the form of probability, and the energy, of course, is a specific formula for it. So the wave functions basically consist of some physical constants and coordinates of the system of the electron, and some quantum numbers. So these quantum numbers are actually the result of the solution of the Schrödinger equation. It's the mathematics. So if you look down there, U and LM. So some people use psi, some people use many different symbols lah. Yeah. So in this case, we will say psi or U. So that we understand that. Yeah. So if it's U, sorry, you can use psi or U. Let me write it there. So you can add a psi. Oops, why is it not? Hold on, let me. Okay. So this can also be psi and LM. Yeah, and it is in the R coordinate, the radial coordinate. So it is, as you can see, this wave function, it consists of the quantum numbers L there, M, and there is no S because this is a solution of Schrödinger equation. S comes from something else. So you have cos theta e to the power of I m phi. So that's the coordinate phi. Okay. So this is what we get, wave function. So using the wave function, we can predict the probability of an electron with a particular energy being at a particular point in space. Wave function is basically, the identity of the system, just like our passport, for example. And from the passport, we can know a lot of other things about ourselves. Okay, so for undergraduates, when we talk about, say, a p or s orbital, yeah. So if it's a p orbital, say for example, this is y called y and this is x. So if we have imagine this in 3 dimensions because there's also a z there. Okay. So this is what we are used to when we talk about p orbitals. Yeah. This is py. Basically, the boundary, yeah, is known as the boundary of the electrons domain. So electrons exist within the boundaries. So these boundaries are actually obtained from calculation of probabilities from the center of the atom outwards. Okay, and if the probability is less than 0.9, you will not draw it, you will not put a dot. But if it is within 0.9, you will put a dot, and what you will see is this. Basically, you put a boundary to it, and you see an orbital, which is really just a construct. It doesn't exist. It is just a construct to say that this is where you can find the electron with a probability of 0.9 or higher within those domains, boundary. Okay, so for a hydrogen atom, we talk about 1 electron orbital. Yeah, so the atomic orbital of 1s, for example, for hydrogen atom, the 1s orbital, let's say it's psi 1s, which is basically psi n equals to 1, L equals to 0, M equals to 0. Yeah, so it's psi 1, 0, 0 lah. That is psi 1s. So this is actually the ground state orbital for hydrogen atom. Yeah, the 1 electron, which is the 1s. Okay, so you will see that later on in quantum mechanics, this 1s orbital or this 1 electron orbital is the basis for almost everything that exists in quantum mechanics. When we talk about calculation of chemical systems, see, it all relies on this 1 electron orbital as the very, very basis. As people develop basis sets, the very basic orbital is the 1s orbital, which is the 1 electron wave function of an electron in an atom. Okay, so this is just to reference some books. They write like this. Yeah, so every time there's a cat, this is known as a cat 100, that means it's a state. Yeah, so there's 1 electron in this particular state. So this is how we say it. So if you talk about this is equal to psi 1s wave function. It is actually a state with the quantum number n equals to 1, L equals to 0, M equals to 0, where 1 electron is actually inside the wave function. Yeah, of course, the 1 electron is distributed around it. So you have to actually think or talk about psi square as the probability density. But that is just quantum mechanics. It's okay. So the most important thing is the solution of the Schrödinger equation gives us these quantum numbers. This is the most important thing. So we have a principal quantum number, orbital quantum number, magnetic quantum number, and a spin. Spin doesn't come from the Schrödinger, but it is a natural extension where you have the spin quantum number S is equals to just half. So these are the four quantum numbers that we all know that results from the hydrogen atom spectrum. And this is hydrogen atom solution for the Schrödinger equation of the hydrogen atom. Yeah. Right. So these are the orbitals. We all know about this. Okay. Now this is where we go into an idea in quantum mechanics, which basically forms the very basic justification of all the labeling system that we see in electronic spectroscopy. Now, in quantum mechanics, there's something called there's an idea called commutativity. Yeah? And it is a very important idea. It says that if two operators commute, then they share a common set of eigenfunction. So, say for example, a normal constant, A times B will always be equal to B times A. Yeah, so it commutes. But when we talk about operators, yeah, operators. Now, just let me just for the benefit of those who are not familiar with the concept of operators. Right. In quantum mechanics, we will have, say, for example, a hydrogen atom. Okay. So this is the nucleus. This is the electron. So this system, it consists of the V. So the total energy is equal to the kinetic energy of the electron plus the kinetic energy of the nucleus plus the potential energy between the electron and the nucleus. Yeah. So we have to convert now in classical mechanics. When we have say for example a planet moving, right, orbiting the sun, and then we ask the question, what is the kinetic energy of the planet moving around the sun? So we will say that the kinetic energy is equals to half mv squared. Yes. Now we can, if we know the mass of the planet and we know the velocity or the linear velocity of the planet moving around the sun, then we can straight away calculate the kinetic energy and we'll give the answer to the person who's asking the question. You see, well, the kinetic energy is equal to something joules or kilojoules. Yeah. In quantum mechanics, it doesn't work that way. So if we have an electron rather than so this is a planet, so it's big. But when we have an electron and we ask the same question, what is the kinetic energy of the electron? It's not as easy as calculating the this time it's the mass of the electron, right? V square, say the linear velocity Vx. So it's not as easy as just calculating the quantity T. But what we have to do is, and this is due to the fact that Mr. Schrödinger some years ago, what he did was he changed the wave equation into a matter wave equation by using the de Broglie equation, which is the P equals to H over lambda equation. So he converted the normal classical wave equation to a quantum equation, and as a consequence of that, we cannot just simply calculate the kinetic energy by just plugging in the numbers m and v into the equation. What we have to do is, in order to get T for electron, we have to first convert the T into an operator. Yeah, where the rule says that every time you see a quantity P, which is the momentum, then you have to change this momentum into minus I h bar d by dx for a one-dimensional case. Yeah. So in this case, so TE will be equal to this is equal to P square over 2m, the x square over 2m. So there's a P, we have to change to this. That means it's minus I h bar d by dx square over 2m, yeah, which will give us in the end T is equal to minus h bar square over 2m d2 by dx square. So So this is an operator because it needs to operate on something. Just like d by dx is an operator, it has to operate on y to give us what we always know as dy by dx lah. So in this case, t is an operator. So same thing with the total energy here must be converted to the operator. So we have something like this, plus en plus bn, en. So everything must be changed to an operator. Once we get this, then we set up the Schrödinger equation and we solve it, and we get a set of energies. In this case, for hydrogen atom, it's just En, and a set of wave functions, which is determined by N, L, and M. Yeah. So the solution of this will give us the total energy of the system, which is the sum of electron kinetic energy, nucleus kinetic energy, plus the potential between the electron and nucleus. Yeah. So, this way. So in this case, we have H psi equals to E psi. And what we are interested in, or the observable that we are interested in when we ask the question, is the total energy. Yeah. Now there are also, of course, other observables for a system like a hydrogen atom. We can talk in terms of the electron's spin, for example. Yeah, as it orbits the nucleus. It's orbiting the nucleus, at the same time it spins. So when it orbits the nucleus, there will be another quantity called angular momentum, or orbital angular momentum. And there will also be a spin angular momentum. So these are also observable. So we can ask another question. What about angular momentum? What about, this is the orbital. What about the spin angular momentum? And you can ask any other, ask any other observable, like what is the momentum, linear momentum of the electron? What is the kinetic energy? Because we are not calculating the kinetic energy alone, we are calculating the total energy, and a lot of other observables that we can actually ask. But the same rule applies. When we ask about an observable, we have to find the operator of the observable and then see whether we can set up the operator operating on the wave function equal to the observable times the wave function. Is it possible? Yeah. So we have to do everything over and over again. But this very important concept in quantum mechanics called the commutativity, yeah, it says that if H, for example, commutes with I is the angular momentum operator. If it commutes, which means if we do this, H hat times I hat minus I hat times H hat, this will equal 0. Of course, operating on something, it will equal 0. So if it is equal to 0, then what happens is that this H here, which results in this wave function psi, yeah, will also, this I will also share the same wave function. So if we were to solve I psi equals to E psi, we will get the same psi. Yeah, it's the same set of psi as the Hamiltonian equation. So it is very important. The idea of commutativity is very, very important in quantum mechanics. Yeah? So if they commute, if two operators commute, say for example the angular momentum operator and the total energy operator commutes, then they share a common set of eigenfunctions. Yeah. Okay. We'll look at that in a more practical sense later on. Now this is what the energy, yeah, for hydrogen atom spectrum. The key is that factor 2, which is the repulsion between electron, is absent. So we only have the interaction between the electron and the nucleus. And due to the absence, yeah, we see that all orbitals with the same n values have the same energy. So we can actually draw the energy levels like so. So for hydrogen atom, we have 1s orbital. Oops. 1s orbital there. Then you have your 2s there. And the 2px, 2py, and 2pz are all of the same energy. So these are degenerate states. Like for n equals to 2, we have 4 degeneracy. And for this is equals to 1. Okay. So any transition you see from the electrons from 1s will go to either one of the p's. Okay. So this is for hydrogen atom. So if n equals to 2, then anything, all the other orbitals with n equals to 2 will have the same energy. So they are degenerate. And this is due to the absence of any electronic interaction. Okay, so that's the energy from the solutions of Schrodinger equation, something that we also know. Okay, this one is nothing. Right, this is how it looks like. Yeah, the energy levels of a hydrogen. Right. So hydrogen atom solution it represents what's known as a hydrogenic atom solution as well, where we're talking about one electron. So hydrogen, helium plus, lithium 2 plus, oxygen 7 plus. These are all two particle system. Yeah, one electron. These are known as hydrogenic atoms. Of course, the treatment will be a bit different because now you know the nucleus has higher charge compared to hydrogen. Okay, so this is something also that we know. The hydrogen atom spectrum is seen to give us different series. If it is n equals to 1 going up, that is known as the Lyman series. Then you have the Balmer series, Paschen series, etc., etc. So this is the importance of quantum mechanics. When the hydrogen atom spectrum was observed in the 19th century, nobody actually knows how it becomes like that, or why is it like that. So Mr. Rydberg actually tried to fit the frequencies using this equation. Yeah, so that is all they know, that this spectrum can be fitted with this equation. But why is it like that? They don't know. So when quantum mechanics was discovered, then they start to understand why the lines are like that. Because now you can actually work out the energy levels of hydrogen atom, and we can explain straight away from the solutions of quantum mechanics the actual spectrum that we see. So we can actually explain the Lyman series, the Balmer series, the Paschen series, etc., etc. Yeah. So quantum mechanics has been applied to spectroscopic observations. This is what makes Schrodinger win the Nobel Prize. Right. So this is something that we all know. Okay. And this is a spectrum of hydrogen atom. Yeah. So the bracket series is very low in the visible. Paschen and Balmer is all in the visible. Then you have Lyman series, okay, where n equals to 1 going up higher, yeah, higher ends, where the delta E goes right into the UV spectrum. So if we look at this one again, so if you look at Lyman, yeah, there you go. So the Lyman series from n equals to 1 going up to very, very high, n equals to 6, right? So that absorption lies in the UV, yeah, because we know that delta E, so delta E is equals to H mu absorption. So for Lyman series, this mu lies in the UV range. Yeah. For Balmer series, for example, delta E equals to H mu S. So this mu here lies in the visible region. Okay, because this one goes from n equals to 2 up to n equals to 6. So the delta E is within the visible region. So this is what we observe in the spectrum of hydrogen atom. Single lines. Can you see the single lines there? One line, one line, one line, one line. Okay. Now the thing is, when we increase the resolution of this spectrum, increase the resolution of the spectrum, we see that actually these lines it consists of two lines. rather than one line. So this one also consists of two lines. So low resolution, you see one line. High resolution, you see two lines. Why is that so? Now, this can be understood if we understand that the Schrödinger equation here does not take into consideration the angular momentum and the spin, angular momentum and spin coupling. So a rotating electron around the nucleus, there are two things that you have to consider. One is the electron is also spinning on its axis, and there is also the nuclear angular momentum with respect to the spin of the electron around the nucleus. So as the electron goes around the nucleus, there is angular momentum with respect to the position of the nucleus, as well as the electron spinning on its axis. So this angular momentum, which we will call L, and this angular momentum, which is a spin, which we will call S, the L and the S are actually interacting. That causes a splitting in the energy level of hydrogen atom. So the splitting of the energy level of hydrogen atom is the one that results in the two lines rather than one single line. So a lot of spectroscopy now is going into this direction, where rather than talking about one line which we can find from the solution of the Schrödinger equation, now we have to consider the splitting of the line because of the interaction between angular momentum and spin, or it's called the you call that orbital spin coupling. Orbital spin coupling. Okay, up to here, is everything okay? Should I repeat anything? Students, perlu diulang atau tidak? Bisa diikut ya?
Bisa dipahami?
Ya.
Bisa, Bapak.
Nah.
Inshallah. Right, so this is what I mean by the splitting. We have a splitting also called the fine structure. So for example, emission from n equals to 2 to n equals 1, you can actually see one line because there is just one emission, but in actual fact, there is a splitting due to spin orbit coupling, and you can actually see two lines in the higher resolution. Okay. But how do we understand these two lines? First of all, in order to understand that, we have to understand the angular momentum. So angular momentum for a rotating body, in this case, we're talking about an electron rotating around the nucleus. Okay, so this is the electron. So the nucleus and the electron is rotating around it. Anything that rotates will have angular momentum. Okay, so angular momentum I is equal to I omega. Sorry, I omega is the angular momentum. Sorry, I here is the moment of inertia. Sorry. So the capital I, in fact, it's not a capital I, it's actually L. This is what I mean. It's not L is equal to I omega. So I is the moment of inertia. Right. So the energy of a particle moving is half mv square, and we change the v to omega r square, and in the end we have the kinetic energy is equal to L square over 2I. I is the moment of inertia. Moment of inertia I. This is all physics, physics. What call that? I, which is this I, right, is equal to mr square. Mass multiplied by r square. So if you have a point there as a center, and you have a mass there, m, and this will be r. And if it is rotating around like that, then the moment of inertia of this particle is equal to m times r square. Okay, and you can actually term the energy, the kinetic energy T, as equal to L square over 2I. Okay. Now, if we compare it with the Schrödinger equation, with the energy of the Schrödinger equation, we see that the energy is equal to L plus 1 times h bar square over 2I, where L here is actually, for quantum mechanics, is the quantum number. So the quantum number of the electron. So we can straight away find what is the kinetic energy, or what is the energy of the say 2p or 2p electron, an electron in the 2p orbital. So the 2p orbital, the L is equal to 1, isn't it? So it's 1 plus 1 times h bar square over 2i, which is equal to 2 h bar square over 2i, and that will be equal to h bar square over I. That is the energy for an electron in the 2p orbital. So L here is directly identified as the quantum number, the orbital quantum number, angular momentum quantum number for the electron. Yeah. So that's angular momentum. The orbital angular momentum, as I've given earlier, yeah, the L is actually equal to the oh, okay, this one is I have to do this again. Right, this is L bold, right, which signifies a vector, and this is L quantum number. So the L bold, so I'll just make it into a bold, is equal to the square root of the quantum numbers, h over 2 pi. So the actual quantum, the actual angular momentum of a 2p particle, a 2p electron, is equal to square root of 2. This is for, this is the angular momentum, the vector angular momentum, because angular momentum is a vector quantity. L gives you the, or it represents the magnitude, and L bold is the vector. Yeah? So the vector is square root 2. The angular momentum magnitude is 1. Okay, so they just say that for a particular electron with the quantum number L, the angular momentum, the orbital angular momentum is given by this, yeah, units. Okay, right. So square root 2 is the magnitude. L is the number that represents the magnitude, which is a quantum number, and the actual value of L is the magnitude, and we will later on look at the vector representation of that particular magnitude. Okay. So it turns out that for electrons, if L equals to 0, s orbital, p orbital, L equals to 1, d orbital, L equals to 2, f orbital, L equals to 3. Yeah. So if I say what is the angular momentum quantum number for a d orbital electron, yeah, say for example d1, right? So this one, L will equal to 2. What about the angular momentum magnitude? This is going to equal to square root of 2 plus 1, which is equal to square root of 6 units. Okay, so this is the magnitude. This is the quantum number for the electron. Let me rephrase that. This is the orbital quantum number, or orbital angular momentum quantum number for the electron, and this is the angular momentum magnitude for that particular electron. Yeah, and you will see that it also has, because it's a vector, you can actually see as well the spatial quantization, or how the electron, in terms of its angular momentum, occupies space. Yeah, right. So you also have angular momentum along the z-axis, the y-z-axis. It's like this. If you talk about something rotating, a human being rotating, yeah, like Sharifuddin rotating. Now the first thing that you will ask is rotating along which axis, isn't it? If you say about a ball rotating, then it's irrelevant. The ball rotates, it doesn't really matter which axis it rotates, it is rotating. You can put any axis to it and it is still rotating. But you talk about a human being rotating, you will ask an axis. Which axis is this person rotating? If, say, for example, I take my body as the z-axis, and you say that, I saw Sharifuddin rotating around or about the z-axis. So that's quite normal. or maybe he is doing ice skating. Yeah, he's rotating about the z-axis, which is across, just right through my body. But if someone comes along, I saw Sharifuddin rotating around the x-axis. Now that is a bit funny. How can he rotate around the x-axis, isn't it? Or y-axis? So rotation, you have to identify with an axis. So usually when we talk about angular momentum, yeah, traditionally, and there is also a quantum mechanical justification to it, you will actually look at the rotation along the z-axis. Yeah, the z-axis. So there is also an angular momentum with respect to the z-axis, or the component along the z-axis. Right. So the component along the z-axis is given by. I'll just write it down. Hold on. Oops. Okay. So the L. This is the angular momentum. Total angular momentum is equal to square root L times L plus 1 units. Okay. And the quantum equation will look like this: L, okay, multiplied by operating on the a wave function, which is the shared wave function, is going to equal to square root L plus 1 times psi. Yeah. So this is what do you call that? The eigenvalue equation. Yeah. So the eigenvalue equation for the angular momentum. So this is the angular momentum magnitude. This is the operator, angular momentum operator, operating on the wave function to give you this quantity here, where inside this quantity, the L is the angular momentum quantum number. Now, this is always a problem when students are presented with this. Yeah, there are just too many variables, too many symbols to remember. Yeah, I give you an example why it is a problem. Okay. But it's okay. It's something that's it's a challenge to students. Okay. Now, so you have H psi. Okay, this is the solution for the hydrogen atom, which gives you psi with quantum numbers n, l, and m, right? Now, H commutes with I, okay, which means that you can also have this equation. Psi equals to square root of L plus 1 times psi, which will give you the, sorry, hold on, which will give you the I, which is equal to square root of L square root of L plus 1. Okay. Now there's also something called LZ. And of course LZ, because it also commutes with H, so you can also have this. What is the number again? Oh, this is just LZ times psi. Okay, where just to make things more confusing, this M is actually equal to LZ. This is ML. Yeah. I hope I'm not confusing you guys. Okay, so in that case, we also have LZ, which is the actual angular momentum component along the z-axis, is equal to LZ. There you go. Yeah. So imagine you have that, and that, and that. Okay, so you have L operator. Now the operator, there is a mathematical form to it, yeah, but it's not something that we want to know. Okay, and this L is equal to square root L plus 1, and then you have Z and an operator, which is also something that you don't want to know. Okay, we are interested only in the results. So LZ is equal to LZ. Okay, so this is the angular momentum quantum number. This is the angular momentum operator. This is the angular momentum. Okay, this is the angular momentum along Z operator, around Z, about Z, and this is the angular momentum about component of it, yeah, Z axis. And LZ is the magnetic quantum number, which can be represented by whatever you have with L. Okay. Am I confusing you? You are free to ask question now.
Silakan kalau ada yang mau bertanya. In English juga boleh, in Indonesia juga boleh.
No problem. Jadi ini seperti bagaimana ya? Adalah seperti menghafal nomor telepon lah. Nomor telepon kalau belum biasa itu ya terlalu banyak nomor kan mau dihafal. Nah, tapi lama kelamaan okay lah. So there are a few. I mean I've got a list of all the symbols just to ensure that students are not confused, right? That represents all the possible quantum mechanical observables for the hydrogen atom. Yeah. Okay. So this is just to introduce to you the idea of angular momentum. Okay. This is just the idea of angular momentum. Okay. Now, this is something that we already know. For example, this LZ here. Now, LZ, you have to remember, is equal to ML. Just to make things more complicated, you have different textbooks defining things differently. Yeah. Let me just try to make it easier. So some textbooks defines, for example, quantum numbers as N, L, and M. That's it. Yeah? N, L, and M. But if you go deeper into this, you see that some books define it as N, L, and M, L. Yeah? And some books define it as N, L, and L, Z. So they are basically the same. The confusion lies on the ML and LZ. Now, same thing as S. Usually we will say NLMS in school, but this one is actually S. Sorry, not S. It's actually MS, and this one is actually SZ. Because there is another quantum number called just S. Okay, just S. This one is SZ and MZ. So what we already know about the alpha and beta spin, the half and minus half spins, these are actually SZ or MS. Because S can only take the value half. So this is the actual spin angular momentum quantum number. Yeah? And this is the spin angular momentum quantum number component about or along the z-axis. Yeah? Component along the z-axis. That is SZ and MS. And this is what we know as alpha and beta spin. Okay. So the angular moment spin angular momentum quantum number is only half. The value is only half. Okay. So the relationship between LZ and L, we all know. For every value of L, there are 2L plus 1 values of LZ. So if L equals to 0, then there's only one value of LZ. If L equals to 1, then you have 3 values of LZ, which is which gives you the 3 p orbitals. Yeah? When L equals to 1. Okay, so LZ, which is the magnetic quantum number, basically governs the direction of an orbital. Right, I mentioned to you just now that L, the thick L, which is the angular momentum for a particular electron, the angular momentum itself. This is given by the value of L times L plus 1 units. Yeah, this is actually the magnitude of a vector quantity. So the vector quantity can be seen here. This is also something that we have actually seen. Yeah. So for example, when L equals to 2, where we have your d orbital, yeah, we will have 5 directions. 1, 2, 3, 4, 5. 5 directions. So the direction is such that with respect to the z-axis, it has to the pointing of the angular momentum have to point to a point on the circle, right? As you can see in the screen. So point on the circle. This is the circle. So this is the circle. So that point there, the projection from the point to the axis. This is the projection from the point to the axis. It has to project to what do you call that? An integer. Yeah. So the only points or the only places where the projection will point to an integer when L is equals to 2 is -2, -1, 0, +1, and +2. So you have 5 LZ for L equals to 2, right? So if you look at this, you can straight away see that for a particle in quantum mechanics, even the space is quantized. You have the energy, which is quantized, the angular momentum is quantized, the spin angular momentum is quantized, even the space, i.e. the vector representation, is quantized. It can only point to certain directions. It cannot point to any direction. So it cannot point anywhere here. You cannot point there. Cannot point there. Why? Because the projection doesn't give you integers. So the only point that gives you integer projection is that point, and that point, and that point. So even the space orientation for a particle which is rotating is also quantized. Yeah? So it seems that it's not just the magnitude is quantized, even the space is also quantized. Right? This is something that I myself, when I look at it and really try to understand what's going on, then I realize that actually, this is something totally new in my understanding, because we learn this in the university, but we don't really understand what it means, you see. So it gives us a very important realization that for a particle that is rotating, okay, microscopic particle that is rotating, just like a gussing, gussing. The gussing, when it rotates like, it rotates like this, right? Okay, a gussing rotates like that. Okay, but it can rotate anywhere it wants. It can rotate in the precession, can be at any point. So it can rotate here. It can also rotate like that. It can rotate down there. It can take any precession it wants. But for rotation of a particle in quantum space, only certain precessions are allowed. Yeah? So that is quite amazing, because these ideas are actually implemented in quantum computers, for example. Okay, these are the list, yeah. So ada sikit saja saya letak. Angular momentum, quantum number, component of the angular momentum, and then the quantum number. But there are a lot of others. Yeah? Right, spin, same thing. Yeah, it is an extension of what we understand of the angular momentum of the orbits. So spin will have only S, quantum number. This is the quantum number S, and can only have a value half, right? So when we talk about an electron in the 1s orbital, the spin quantum number, the spin angular momentum for that particular electron is equal to square root of half plus 1, which is equal to 1/2 square root 3. Yeah. So that is the spin angular momentum. The quantum number is S. and it can only take the value half. And we also have SZ, which is going to be either half, minus, or plus half. Okay, and this is the component SZ, the component of the spin along the Z direction, along the Z axis, right? And we also have this idea of multiplicity, 2s plus 1. So if we have 1s there pointing up, yeah, so the multiplicity is equals to 2, right? Because it's 2 times half plus 1, which is equal to 2. If we have something like this, say two orbitals with parallel spins, so the multiplicity will be equal to 3, yeah, which is a triplet state. If it is paired, this one is actually going down like that, then the spin is equal to half plus minus half. Yeah, so its multiplicity is equal to 1 for this. Okay. Right. Why are we doing all this? Yeah, we are doing all this because the fact that energy levels can be split due to spin orbit coupling means that we have to find the best ways to label the states. What will be the best labeling system? Now, it turns out that electronic spectroscopy, the understanding of what's going on, or understanding the spectroscopic phenomena that is happening, is very much dependent upon the what do you call that? The type of labeling that we have to put in, because or else we will be very, very confused. There are just so many states, so many different possibilities that without labeling, it will just be a mess. So now electronic spectroscopy moves, the understanding moves towards how to label the energy states, yeah? How to actually label them. So we know that labeling depends on N, right? It depends on L, and it depends on L plus S. It depends on the coupling between the orbital and the spin angular momentum. So now we have to work out how are we going to label states based on this understanding. Okay, nak berhenti 5 minit ke? Mungkin berehat sebentar.
Ya.
Jadi kalau ada soalan-soalan terakhir gitu, gimana?
Boleh. Ada yang mau bertanya?
Please ask, ini it's okay.
Pak, saya mau bertanya, Pak.
Ya, baik, silakan.
Ya, buat yang di bagian di bagian spektrum dari atomic hidrogen, ya, tadi sempat dibahas kalau untuk spektrum ini bisa menghasilkan two line kan, jadi 2 line. Yang berarti Schrödinger equation ini tidak memberi consideration into angular momentum dan spin coupling. Jadi, is there any possibilities that 2 line tadi akan berubah menjadi 3 atau dan bertambah seterusnya gitu, ketika ada sesuatu faktor yang diaplikasikan ke dalam si spin tadi. Jadi kan tadi itu di angular momentumnya ketika dapat energi itu kan ada spin coupling. Nah, terus dari line itu berubah jadi 2 dari yang satu yang tidak didasarkan oleh Schrödinger equation. Nah, jadi apakah bisa line tadi berubah menjadi 3 atau menjadi quadruple, mungkin jadi 4 dari 2 kali 2 dan seterusnya mungkin, Pak?
Sebenarnya bisa.
Oh, bisa.
Iya. Itu apa namanya ya, saya lupa efeknya ya. Itu kalau kita letakkan sebagai contoh atom itu di dalam magnetic field, ya. Jadi kalau diletakkan dalam magnetic field, dia akan berlaku splitting lagi. Gitu.
Oh, berarti ada kayak energi tambahan yang mendasari splitting lebih lanjutnya ya, Pak?
Ya.
Oh.
Ya, splitting itu biasanya begini ya. A splitting happens when there is a perturbation to the line. Yeah, some disturbance to the line. Now, the disturbance may cause the line to go up or down, okay? Or it can split to 2 because there are 2 possibilities due to the perturbation. Yeah, so 2 possible states due to the perturbation. Kita akan lihat kemudian ini bagaimana apa yang saya maksudkan dengan these states ya. Karena kalau kita letakkan atom ke dalam magnetic field, itu bisa splitting lagi. Sebentar saya lihat dalam internet. Saya udah lupa. Bentar ya. Ya, dipanggil Zeeman effect. Pernah dengar nggak?
Belum, kebetulan.
Belum ya?
Ya.
Jadi itu bisa saja. Kalau tiada magnetic field, itu bisa dilihat itulah terms itu kan. Tapi bila dalam magnetic field, itu bisa itu lagi masih bisa splitting lagi. Ya. Tapi kita sekarang ini berbincang mengenai satu elektron. Satu elektron saja. Jadi yang p orbital akan split jadi dua. Kita akan lihat bagaimana itu bisa split ya. Jadi ada satu level sebagai contoh p level, it will split into two different energy levels. That causes that causes you to see the two lines kan. Ya. Tapi itu untuk satu elektron. Jadi kalau untuk banyak elektron, dia splittingnya ya seharusnya banyak splitting gitu ya. Karena ada more possibilities. Jadi so things can get a bit quite complicated. But there's always a rule. Quantum mechanics gives you the rules of how to actually come up with all these different energy levels. Nah, sebelum kita berhenti, just to end this, before this I talk about electronic states kan, energy states, and how the energy states are split because of the interaction between orbital and spin coupling. Semua ini menghasilkan apa yang kita panggil sebagai spectroscopic terms. So kalau sebelum ini kita gunakan energy level, now we can label the energy level easily because we are just using s orbital, p orbital dan seterusnya. But as things get more complicated, you get more splitting due to the spin orbit coupling, then what you get from the splitting is what's known as spectroscopic terms. So now you are labeling these energy levels as a new name called terms, spectroscopic terms, because there are many possibilities. So we are trying to label all the possibilities. So once we have labeled all the possibilities, we look at the actual spectrum, we see some lines, then based on the possibilities, we can assign these lines. So that is basically the idea.
Okay, so it depends on the atomic itself, yes, Prof.
Yeah.
So
the Zeeman effect, we're not going to look into it lah, because it will get more and more complicated, and we have more time to explain.
Okay, ya, Prof. Terima kasih banyak, Prof.
Oke, sama-sama. Jadi insya Allah kita berhenti sebentar.
Boleh kita rehat.
So kembali jam berapa?
10:15 boleh? Atau 11:15?
10:15 boleh. 11:15 di Malaysia lah.
Ya, 11:15 Malaysia lah. Berapa menit? Untuk rekan-rekan mahasiswa disiapkan aja ya pertanyaan, itu ditulis aja dulu supaya tidak lupa.
Okay, kita bisa kita teruskan.
Ya, ya, silakan Prof.
Okay. Okay, so I mentioned earlier about spectroscopic terms. Yeah? Now, this is important because when we talk about electronic energy levels, we also think about electronic configuration. Yeah. So if we have, say, for example, 1s, so 1s and 2s level, for example. So we will also think about, okay, how do we fill in the electrons? So say, for example, for hydrogen atom, we have 1s electron, and for helium, we have two 1s electrons. So we have 1s1 for hydrogen, 1s2 for helium. Yeah, that means we fill it in so that we know that we have a configuration. But we know when we reach like P or D, there are many possibilities for two electrons. Many possibilities. So that is one, and the other one is we don't know about angular momentum or spin configuration because of the different possibilities. Yeah. So, for example, in this case, what about a 2p2 configuration? So we know that for 2p2, n is equals to 2, m or l, z equals to 1, -1, and 0 because because l equals to 2. Yeah. And we have ms or sz equal to half and -half. So there are a few descriptions that we can think of. This description, that description, okay, this description, and there are more actually. For example, we can also have something like that. Yeah. So the point is, when we talk about electronic configuration, 2p2, it doesn't tell us of the different possibilities of other configurations that we have to take into account. It's L or it's SZ, LZ or SZ. So these configurations are called microstates. Microstates. So there are many microstates for a particular electronic configuration. So each microstate represents a possible electron configuration, and we can see that these different microstates can vary in energy even, because when we talk about two electrons which are parallel or anti-parallel, the inter-electron repulsion will be different. Yeah? So the groups of this microstate, so you can have a few microstates with the same energy or a few microstates with different energies. So groups of microstates, if they are the same, they are called terms. Yeah? So you may have a particular so 3 or 4 microstates with the same energy. So you have one term. Yeah. Another microstate, 2 of them, same energy, that's another term. Yeah. So we have microstates and we have terms. Okay. Now, there's another issue. I think I'm not sure whether you have done this. Maybe you haven't reached that point yet. In spectroscopy, you have to learn about term symbols. Yeah? Term symbols basically represents the labeling of the different electronic states that can exist. Yeah, due to the different possibilities of arrangement of of electrons within your atomic orbitals. Yeah. So the term symbol is given by this. Yeah? You have 2s plus 1, which is the multiplicity. You have x, which depends on the orbital angular momentum. Okay, so for L equals to 0, you have large S. L equals to 1, you have P. L equals to 2, you have D. And finally, you have this J there. J is basically your spin orbit coupling. Yeah. So by using a term symbol, you can actually expand the labeling. Yeah. So if you have 1 electron or 2 electron in the p orbital, say for example, say that configuration. Yeah. So that configuration is a 2p2 electronic configuration. Now, if you are just thinking of in terms of 2p2, you can only have one energy level, right? 2p2, that's the state. But of course, 2p2 has many configurations. So what we want to do is we want to split the 2p2 into many different configurations. Yeah. So you have a 2p2 there, and you have different energy levels that may come about due to the existence of many possibilities of microstates. Yeah. So how do you label this? In order to label that, we use the term symbol, which is basically 2s plus 1 x j. Yeah. So yeah, that is how we solve the problem of labeling the different groups of microstates. Yeah? Right, spin orbit coupling, I don't have to talk about it. This is something which is known. Yeah. Okay. So what I want to point out is the strength of the spin orbit coupling depends on the nuclear charge. So there are many ways of doing spin orbit coupling, but it all depends on the nuclear charge, because there are two ways actually of doing it. And the best ways depends on which nucleus are you talking about. Yeah? So that one is another issue. Right. So what comes after this will be a lot of maths, well, not really maths, like just different ways of combining J, L, and S. Okay, different ways of combining L and S. We know that one of the reasons why the energy levels split, at least for the first part, the spin orbit coupling, is the reason why there occurs a splitting. As we have discussed before, if you put the whole system into a magnetic field, you will see further splittings. Yeah? But we won't go into that. We'll just stop at the spin orbit coupling. Yeah? Now, when we say spin orbit coupling, what do you mean spin orbit coupling? Yeah? We know that there is a angular momentum due to spin, angular momentum due to orbital motion of the electron, but how do we actually, combine the spin orbit coupling? Now, this is where quantum mechanics and some knowledge of maths would actually help. Yeah? In order to do spin orbit coupling, we have to realize that the orbital and the spin angular momentum are actually vector quantities. Yeah? So when we do a coupling, we have to couple based on vector. So it's a vectorial coupling. But we don't like to, work in terms of vectors. Yeah? Because it's going to be a mess. You have to draw your lines, and stuff like that. So we have to find ways to actually do things better and do things easier. You will see that as you go along. If you look at any quantum mechanics textbooks, they will show you a few ways of doing it. I stick to one way, which I feel is very easy for me to do. Yeah, it's very easy to do. And I rely on that method to actually come up with all the different term symbols for different types of electrons. There are two types of electrons. One is what is it called? We'll come to that. Suddenly I forget about that. Where you have two electrons which are similar and electrons which are not similar. But the word is not similar. It's equivalent, right? So you have non-equivalent and equivalent electron. But that case is only for atoms which has more than one electron. We are looking at only hydrogen atom. Yeah, even with hydrogen atom, we have this splitting, right? So we want to know how to actually do the splitting and how to label the energy levels, the terms. So spin and orbital angular momentum can be combined vectorially, okay, to give the total electronic angular momentum, which is J. So that's another quantum number. We have this J, right? So J, bold J, okay, this is the total angular momentum, Yeah, total electronic angular momentum. Total electronic angular momentum. And you also have J hat, which is the total electronic angular momentum operator. And we also have J Z, which is the total electronic angular momentum component about Z exists. Yeah. And what else is there? And of course J, the quantum number, yeah, the total electronic angular momentum quantum number, and JZ as well, which is the team quantum number Z. Yeah. So it's the same set of all these symbols, the same as for L, the same as for S. Okay. Right. In this case, if you look at this, this is the J, the actual electronic angular momentum itself. Yeah? So since J is a vector quantity, it's actually a vector addition between L, which is the angular orbital angular momentum, plus the spin angular momentum. Okay. Right. So you also have J. You see J. This is the J angular moment, J quantum number. It gives you this, which is the this J here. Right. So this J here is basically square root of J plus 1, and this J is the quantum number. And you also have a component Jz and the quantum number for the Z component. So basically, in order to study the spin orbit coupling, yeah, we have to do this. We have to add L and S vectorially. So there are many ways of doing it. If you look at this, yeah. Now this is this is the spin plug. So spin again is the same thing. You have S and SZ. Spin doesn't change. In fact, spin doesn't change until you reach to the molecule. When you want to label energy states due to molecules, spin doesn't change. Spin is always commutes. Spin will always commute with the Hamiltonian, be it for hydrogen atom, for big atoms, for diatomic molecules, for big molecules. Spin will always commute. That means for labeling electronic states, spin is always consistent. So you don't have to worry about spin. The only problem is the angular momentum. Soon, angular momentum will no longer commute with the total energy. So you can't use the angular momentum quantum numbers to label anymore. But for hydrogen atoms, you can still do it. For atoms with more than one electron, you can still do it. Okay. So there are many ways of doing L and S combination. Yeah? I don't want to go through this because I think this you can actually do it in the textbooks. Yeah? So there's one way, summation of the Z component. The other one is you can either reinforce L plus S or oppose L minus S. Now this is the way that I like. This is how I like to do it. Using the Z component is a bit difficult. Yeah. Okay, so let's have a look at the example, because it will be easier to understand if we were to do it actually on the blackboard. Okay. Now let's have a look at hydrogen atom. We are only interested in hydrogen atom now. So hydrogen atom, the configuration is 1s1. So you have 1s orbital with 1 electron there. Now an excited hydrogen atom, yeah, because 1s can only go to 2p, right? S can only go to 2p, to p. S to S is not allowed. So you have S to P. This one is not allowed. This is allowed. So the next excited state of hydrogen will be 2p1. So you have a 2p and you have 1 electron there. Okay. So let's have a look at this case first, because we still have to study the spin orbit coupling, right? So for the first case, right? For the first case, the electron has a quantum number L equals to 0, and the spin can only be half. It cannot be minus half because there's only 1 electron. So it can only be half. Yeah, only 1 electron. Because if there are more, then there's another half. Each electron will have a spin quantum number half. So if there's another electron, there's another half. Another electron, that's another half. Yeah. But now we're only talking about L equals to 0, S equals to half. Right. Now for this case, you have L equals to 1, S equal to half. Okay. So how do we actually do? How do we, now let's have a look at the spin. How do we do the spin orbit coupling? So remember, if we were to label this state, this part here is going to be something like this. Yeah. So 1s there, you have 2s here, 2px, 2py, 2pz. So we're talking about this kind of transition. Yeah. Maybe it goes to px, py, pz. It's okay because it's all degenerate. Yeah. So this will result in, we'll just take px for example. 2px, this is 2s, this is 1s. So it goes there and you have one electron there. Okay. So that's the second case. So in the first case, we want to come up with the electronic term symbol because we are going to do the spin orbit coupling now. Yeah. So it has to be 2s plus 1 x j. Yeah. Now 2s plus 1, s is half, there's only one electron. So you have 2 up there. L equals to 0, that means you have s. Yeah. And j is actually just L plus S. There are no other possibilities. It's just L plus S. So it's going to be half there. So it's 2s half. This will be the term symbol for the ground state of hydrogen atom. 2s half. Yeah. What about this? What about this one? So we have again 2s1, s is always half. So it's 2. Okay. X depends on L. Yeah. X depends on L. But of course, we're not talking about the 2s. We're talking about 2p. Hence, it's just 1. Yeah. So it will be p. Yes. Now the problem is this one. It's half, 1 and half. Because we have to do L plus S. Yeah. So the key is this. The J is going to be equal to L plus S until the modulus of L minus S. Yeah. So L plus S is 3/2. Okay. For one electron, it's just straight away L minus S. But if there are many electrons, you will see there are many possibilities in the middle. Yeah. But don't worry about that yet. So L minus S is 1 minus half is going to be just half. So there are 2J here, which means that we have 2P half and 2P 3/2. Which means if we were to this is your 2P, this is your 2S, this is 1S. So a transition to 2P, and in the spectrum, it will look like this. It's 1, 9. Okay, and this is this transition there from 1S to 2P. But after spin orbit coupling, we will have 1s. Now we don't want to use 1s because we have already determined the spin, the electronic terms. Yeah, term symbols. It's going to be 2s half. Okay, and for this one, there will be 2 energy levels. Right, this is going to be 2p 3/2 and 2p half. So now there are 2 possibilities of transition from here to here, or from here to here. 2 possibilities. After we have determined the spin orbit coupling. So now what you see are two lines. Okay, so this one, if this is frequency, intensity, that means this one will be the lower frequency. So is this transition, and this one, which is the higher frequency, higher energy, is that transition. Okay, so the key is how we actually do the spin orbit coupling. Now there are two possibilities of spin orbit coupling. One is the it's called the JJ coupling, and the other one is called the Russell-Saunders coupling. Usually you just see RS. Okay, so most of the time I prefer Russell-Saunders coupling. Now JJ and Russell-Saunders, they are different. It works for certain systems. JJ works better for certain systems. RS works better for certain systems. But if you just want to, for the sake of learning, conceptually understand what's going on, we use the RS, Russell-Saunders coupling. Yeah, where what we do is we actually do the total orbital first, total spin first, then only we do the coupling between L and S. Yeah, so that is Russell-Saunders. This is standard text in any quantum mechanics or spectroscopy books. So what we did was just now is we need to calculate the J, which is going to be L plus S up to L minus S. Because there's only one electron, we don't sum it up, so we say it's L plus S to L minus S. Yeah? And this is going to be the J, one electron. Because when you talk about many, then you have to sum up. So L becomes the sum of Li, and S will become the sum of Si. Of course, in doing the summation also, there are rules. Now, this is just a simple summation, right? But there are also rules. So we will look at it when we look at the many atoms, atoms with many electrons. Okay. Right. I hope that's clear. Is that okay? So the spin orbit coupling results in the splitting of energy levels of a term, and this information can be used to label states arising from spin orbit coupling of an electron in various orbitals. Yeah? Okay. So that is how we actually come up with the term symbols. Yeah, term symbols. You can also look at it in terms of microstates. Yeah? In terms of microstates. Yeah. So an electron in a p orbital, so S equals to half, L equals to 1, will give rise to two term symbols, which is 2p half and 2p 3 over 2. And the number of microstates is actually equal to this. So this is something new. The number of microstates is 2s plus 1 times 2l plus 1, which is equal to 6. Yeah. Now, the best way to look at these microstates is to actually do it in a table. Yeah. So you have Lz, which is equal to plus 1, 0, and minus 1. Yeah. So this one is basically your 2pz, and this is your 2p. Plus 1 and minus 1 are not your 2px and 2py. 2px and 2py are actually a linear combination of the different Lz. But anyhow, we are looking at it in terms of quantum numbers. So how many combinations are there for Lz with respect to Sz? So Sz can only take half and minus half. Okay. So one electron, right? One electron can either be up or it can be down. So how many different possibilities are there for the ups and the downs to go along with the plus 1, 0, and minus 1 Lz? Yeah? So you put it inside there. If it's half-half, it's 3 over 2. If it's minus half plus 2 plus 1, it's plus half. If it is 0, then it's just minus half and plus half. If it is minus 1, then it is -12 and -3/2. Okay, so there are 6 microstates, 6 different electronic states. But some of the electronic states can have same energy. For example, if you talk about this and this, they are the same, isn't it? Right? And this, they are basically the same. Yeah, same energy. And this is also the same energy. So they are different microstates, but they have the same energy. Up and down at any different states is going to be the same energy. Yeah. So there are different microstates, but they may have the same energy. Okay. So this is where we get the fine structure of the hydrogen atom, as I've mentioned earlier. Is due to the presence of different energy levels, which is due to the spin-orbit coupling. Hydrogen is 1 electron. Thus, the splitting observed is only for hydrogen. It's a doublet, doublet splitting because there's only one electron, and the doublet causes the J to be split into 2. And the selection rule, what is allowed and what is not allowed for the transitions. Delta N, it can be anything. N equals to 1 to N equals to 2, N equals to 2 to N equals to 3, it is okay. For N equals to 1 to 3, no problem. Delta L can only be plus minus 1. Yeah? So S can go to P. S cannot go to S, for example. Yeah? And delta J can be 0 or plus minus 1. So the transitions, the possible transitions are this: 2S half going to 2P half. That's possible because delta J is equal to 0. 2S half to 2P 3/2, delta J is plus minus 1, that's also possible. So there will be 2 possible transitions from the ground state of hydrogen. This is where you see the hydrogen fine structure because of the splitting of the splitting of the p orbital into 2 electronic terms. And this is the best way to see it. Yeah. So the 2p breaks into 2, 3p also breaks into 2, 4p breaks into 2, yeah, and D also, yeah, breaks into 2, yeah, 5/2 and 3/2, yeah. No, these two are not relevant. These two are out of place. These 2 slides. That's also out of place. Okay. Anyhow, so now we know that since the angular momentum and the spin as well, operators commute with the 1 electron Hamiltonian operator. This provides a technique for obtaining a consistent classification of energy levels because we can use I and S to label electronic states. Yeah? So they share eigenfunctions and also they share quantum numbers. So we've looked at that. And these quantum numbers can be used as a method of classifying energy state that results from the solution of the Schrödinger equation. Yeah. Yeah. Any questions?
Yes, silakan kalau ada pertanyaan. Terkait dari sistem simbol, kemudian yang lain.
Ada persoalan?
Nah, ada yang mau ditanyakan? Ada yang kurang jelas? Yang belum paham?
Jadi kuncinya di sini ya, kuncinya. Atomic term symbols which are generated from the knowledge of the electronic angular momentum atoms are used to label atomic electronic states. Yeah. Jadi ini semua datang daripada mana? Datang dari the fact that the Hamiltonian operator commutes with the angular momentum operator. So that means they share the same eigenfunctions, which means that they share the same quantum numbers, which means that you can use quantum numbers that you obtain from angular momentum to label the hydrogen atom electronic states that arises from the solutions of the Schrödinger equation. Yeah. Jadi kita tidak perlu bersusah-susah. Yeah, we just use the quantum numbers of the angular momentum in order to label the energy levels of the electronic energy levels. Yeah. So kebanyakan dari analisis yang berlaku selepas ini and the labeling is due to the angular momentum. So by looking at angular momentum, you can already label energy levels that comes from the solution of the Schrödinger equation for hydrogen atom. Okay.
Ada pertanyaan? Ada yang ingin bertanya? Oke.
Yang penting ni harus faham, jangan tak faham. Ya, students dia biasanya dia kalau dia faham pun dia tak bagi tahu. Dia tak faham pun dia tak bagi tahu. To me, I mean, this is very important. I see a lot of students find this difficult because it is difficult, some of them just leave it. But it turns out that when they go up, say for example, if you are an inorganic chemist, for example, you're an inorganic chemist. Inorganic chemists will do a lot of spectroscopy, isn't it? You will do a lot of spectroscopy, and you have to label this. You have to what you call that? Assign peaks, right? When we talk about say metal complexes, again, you have to assign peaks. You have to know this transition is due to what, yeah. And you use all these labels, and you don't understand these labels. So in the end, you know, you don't have a good grasp because you don't have a good grasp of what's going on in spectroscopy. You will not be able to really understand what's going on. Yeah, all the symbols and everything. You know. For example, you want to look at a simple concept like crystal field splitting, crystal field theory again. In a crystal field theory, you use symbols like T2G, EG, dan seterusnya, kan? And I know many students don't understand why these symbols are like that. Why are they these symbols? So it's very important that you try your best to grasp these ideas. Ada soalan?
Ada yang kurang jelas? Ada pertanyaan? Halo? Bisa dipahami?
Oke, kalau tak ada tak apa, no problem. Oke, sebelum kita berhenti, saya ingin teruskan sedikit supaya memberikan momentum kepada kita lah. Ya. The question of why, what about many electron atoms? Yeah. We've seen how to come up with term symbols using one electron, which is the hydrogen atom. What about many electrons? Now you have to understand this. The Schrödinger equation can only be solved exactly for hydrogen atom. It can only be solved exactly for hydrogen atom. So when we use angular momentum labels to label what we see in the spectrum, it makes sense. You see two lines, for example, in hydrogen atom spectrum. When you take the spectrum at higher resolution, you will know that this is due to the fact that the p orbital is split into two term symbols. Yeah. Now you don't know about this from the hydrogen atom solution that you get from Schrödinger equation. So by considering the spin orbit coupling, in which we only play around with the quantum numbers, we can already assign the spectrum, even without looking at the solution of the Schrödinger equation. So just by playing with the quantum numbers, knowing that these quantum numbers can be used to label electronic states, we can already have a picture in our head of where these two lines come from. Which means that for many electron atoms, where you don't have a solution for many electron atoms, you don't have the Schrödinger equation solution exactly for many electron atoms, you can still understand the spectra of many electron atoms just by understanding the spin orbit coupling, yeah, and playing around with the quantum numbers. So this is a very powerful concept. Yeah? It's not, you don't even have to use Gaussian, solve the equations, Schrodinger equation and come up with, you don't have to use Gaussian, you just use the, play around with the quantum numbers, right? Understand spin orbit coupling, come up with the energy levels, the term symbols, and then compare it to the spectrum that you obtain. And you can actually explain the spectrum just by using labels that comes from angular momentum. Okay, so this is a very powerful concept, and if you apply it to many electron atoms, you can explain a lot of things. Yeah? For example, you want to understand lasers. Yeah. So you just search in the internet something about lasers. Let me have a look here. I'll just search for you. No. See if we can get. I couldn't find a good example. I'll just bring it here. Okay. You see some of the laser systems like this, right? This is helium neon laser and ND-YAG laser. So in order to understand these lasers, you have to actually know about the energy levels, which are the term symbols. See? So you use 3p4, 2p4, and these are not obtained from the solutions of Schrodinger equation. These are actually obtained from our understanding of, say, the neon energy neon atom, the spin orbit coupling of the neon electrons, yeah? And say, for example, for the neodymium atom, yeah, and the spin orbit coupling of neodymium atom, that allows us to understand, what kind of lasers can be produced. Yeah? Of course, the energy is different energy. You have to do the calculation. I'm talking about the labeling, and you can actually label and put the energy levels in the right position, and actually understand what's going on with the spectrum that you see. Yeah? So it's a very important and very powerful concept. Okay, what about many electrons? Because this is the more practical thing. Well, hydrogen is not very practical, but it gives us some idea of how to come up with the basic concepts of how to do this. So what about many electrons? Okay, so the first thing that we have to ask is, do the angular momentum, the spin and the orbital angular momentum operator commutes with the Hamiltonian? Do they still commute? Yeah, because the one that we did with hydrogen atom, we are only talking about one electron wave function. So what about the total many electron Hamiltonian? Now it turns out that yes, they still commute. Yeah? So we still find that these are all valid eigenvalue equations, because the other eigenvalue equation that we are interested in is the H psi, right? Equals to E psi. This is where all the solutions come in. So this psi is the same as this psi. It's the same, yeah, because the operators, they commute. Yeah? So we can still use the same idea as we worked out for the hydrogen atom. Okay. Now what we have to do is we have to add the angular momentums, and we have to find good ways to add them. Yeah. Now, as I mentioned earlier, there are two types of electrons. One is the non-equivalent, and the other one is equivalent electron. Non-equivalent here means that they are in different N or different L. For example, we have, say, I'm going to give you a configuration like 2p1, 3p1. So you have 2p1 here and 3p1 here, and one electron each. Okay. Now those two electrons are non-equivalent. Okay, because there are also cases where you have something like this. Yeah. 2p2, sorry. Yeah. Two electrons in the same orbital. Now this is equivalent. Yeah. Now equivalent is quite not difficult, but it's apa ya, bahasa Malaysia kita panggil leceh. Bahasa Indonesia apa ya?
Apa?
Leceh. It's so cumbersome. To do it is so cumbersome. There are so many things to do. It's not difficult, but leceh.
Oh, sorry.
Apa ya? Cumbersome.
Simple, tapi itu rumit gitu ya.
Rumit lah. Rumit. Jadi rumit. Bukan kerana susah, tapi kerana banyak yang nak kena buat. Jadi kalau kita nak dapatkan the term symbols for equivalent electrons, you have to do all the different microstates and work out which microstates belongs to a group, which one doesn't belong to a group. Yeah. So I just leave that. Usually I just say, if you want to understand the concept, you will just work on non-equivalent electrons. It's much easier. Yeah. So two electrons which are not equivalent. They are in different energy levels, different orbitals altogether. Yeah, different N or different L. Okay. Right. So what we have to do is we have to first couple the individual orbital angular momentum, yeah, by adding L1 and L2. Then we get the total angular momentum. We do the same for spin, yeah. Later on, we do the same for spin, and then we get the total spin angular momentum. Yeah. For example, in this case, 2p1 and 3p1. Okay. L1 and L2. This is the way to do it. The total L is going to be L1 plus L2 until L1 minus L2. Yeah. So for the case of L1 and L2 equals to 1, you have 1 plus 1. Okay. And then you have 1 plus 1 until 1 minus 1. So this is equal to 2, this is equal to 0. Whatever in the middle, you just put in. Yeah. So you have 2, 1 in the middle, and 0 at the end. So L will be 2, 1 at 0. Okay. So straight away we know the X. The X will be L equals to 2. That means it's going to be D. Another one is going to be P. And another one is going to be S. So what we have to add now is the 2S plus 1 up there. Yeah. Okay. So we start off with the summation of the L. So this is just a apa ya? Dalam bahasa Indonesia, cikal bakal of what is coming. Gitu ya. Jadi notanya sudah saya berikan link. Saya akan buat sedikit perubahan kepada nota minggu hadapan dia ada sedikit tambahan di hujung-hujung lah.
Ya.
Itu saja. Gitu. Oke, saya rasa sampai di situ dahulu.
Iya. Terima kasih Prof. Syarif. Thank you very much. I think because of this already elephant, so we don't have any question from student, right? Mungkin karena sudah jam 11 tidak ada pertanyaan lagi ya, mungkin kita lanjutkan insyaallah pekan depan gitu ya. Nanti insyaallah kita diskusikan dengan Prof. Syarif karena besok tidak bisa Prof. Syarif ada agenda yang lain, mungkin insyaallah mungkin hari Isnin atau Selasa Prof. Syarif ya.
Kalau hari Rabu bisa juga.
Wednesday sudah ini ya Pak, Idul Adha, sebagian Idul Adha.
Oh iya, udah Idul Adha, ya benar. Itu terpulang kalau mau hari Senin, Senin bisa juga. Ya. Ataupun mungkin lepas Idul Adha gitu, kalau mau disambung lepas Idul Adha, mungkin lebih segar lah pemikirannya.
Kalau Prof. Syarif kosong pekan depan hari Isnin dan Selasa?
Hari Isnin insya Allah. Hari Selasa juga insya Allah.
Pukul berapa kira-kira?
Dalam waktu seperti ini juga lah.
Nah, pukul 10 ya, pukul 10 waktu Malaysia ya.
Ya insya Allah.
Ya. Mungkin hari Isnin saja Pak Syarif karena biasanya setelah Idul Adha banyak activity itu, motong sapi, makan itu, jadi lama recovery-nya. Baik, makasih banyak Prof. Syarif yang sudah menyampaikan sebagian dari elektronik spektroskopi. Kita terakhir sampai kepada tem simbol gitu. Sebagian sudah kita pelajari juga ya di kimia koordinasi tem simbol. Mudah-mudahan bisa di refresh lagi sehingga demikian ketika kita bicara elektronik spektroskopi dalam aplikasinya nanti bisa lebih jelas dan lebih bisa menguasai. Sekali lagi makasih banyak kepada Prof. Syarif, mudah-mudahan diberikan kesehatan dan bisa membantu kita juga untuk menjadi guest lecture di kuliah-kuliah kita di Unpad.
Amin.
Ya, amin. Ya, kemudian makasih banyak juga kepada ibu-ibu bapak-bapak yang sudah hadir, yang sudah menemani kita juga. Mudah-mudahan ini juga sebagai bentuk supporting kita kepada mahasiswa dan juga untuk refresh juga bagi kita terhadap hal-hal yang kadang-kadang kita tidak suka nih Prof. Syarif itu terhadap kuantum mekanik dan segala macam ini kurang diminati gitu, tapi harus kita pelajari juga gitu. Baik, terakhir mungkin kita akhiri dengan mengucapkan bersama-sama alhamdulillahirabbil. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Terima kasih Prof. Gimana kabarnya, sehat?
Alhamdulillah.
Yo.
Bagaimana? Sehat?
Alhamdulillah. Insya Allah nanti ketemu ya Prof.
Jadi kita bincanglah bila yang waktu paling sesuai.
Iya. Silip.
Oke, terima kasih.
Sama-sama.
Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam
Warahmatullahi
Assalamualaikum warahmatullahi wabarakatuh. Terima kasih banyak, Prof.